we go. All right, I have some announcements / we gotta take care of stuff. So if you haven't signed a field trip permission forms, I need those like yesterday, really. So field trip forms, even if you're not sure if you're going, it's better to fill in a form and then not go than you try to show up. And so the reason why I need them now is because they have to be emailed to somebody else, and so you know how things go, so I need those ASAP. And then, let's see, I also need to see that Jacob and Adrian aren't here, because I need to finish. I have, like, all the scores for your Earth Day project, but then I never put them in, because I'm missing sources from some people, and so I was trying to get those done. So your group, Amanda, Yahira, I need sources from your group as well, your group of 4. So I don't know if you have sources. So if you could get those to me like ASAP, like today, just so I can put in the grades, because I'm just sitting on all these. And then, yeah, Josue's not here. Logan, you're in the chat, so I'll type it to you, but if you have sources, I need those to finish that. Okay. So field trip forms. And then I'll just put Earth Day projects should be getting back to you. And they really were fine, the grades on that. Like I just said, I was just missing some sources from a few people and trying to hunt that down. What else? Oh, and then some more things. Let's see. So I have quiz 2 to give back to people, but yeah.
I was just wondering if there was like a minimum requirement for those sources on that project?
I don't think I stated anything, but like I at least need some sources. Yeah. And of course, the more the merrier that you used. So I'm missing a lot of quiz 2 from people, and so that was a take-home quiz. So there's still a lot missing. So just get those in, again, ASAP. I know I'm pretty lenient with the deadlines, but you're going to hurt yourselves later. That's all I have to say. Is it doesn't really benefit people to procrastinate, is what I've noticed. Again, I don't want to penalize people. I understand stuff happens and you get behind, but we still got to get it going. And then so quiz 3, I plan to hand back to you, but I left it on my dining room table. So I only have 2 people's quizzes that I graded, not with the rest of y'all. But I wanted to point out number 1, because I ended up throwing out that question. So it was that one, which of the following is not a form of energy? And I at least wanted to go over what I was looking for or thinking. And so the thing that I was going for is, of course, right, entropy is just a measure of disorder. So that's not energy. But then I was looking for enthalpy as being a form of energy, since it's at least the measure of the internal energy plus whatever is available to do work, so your pressure-volume relationship.
But how is that a form of energy if it's a measure of energy?
That's why I threw out the question.
Oh, okay.
Because the overwhelming amount of people put no, they were both not forms of energy. So then upon thinking about it, I assumed that people were thinking of forms of energy of like kinetic, potential, and not thinking like this. So it was a bad question. People were already confused with the double negatives anyways. So everybody who like didn't circle both also put neither, and it was just, I just threw it out. So that's what I was going for. Bad question, because yeah, you're gonna argue with me that it's not really energy. It was a bad question. So it just got thrown out. Everybody got full points for that. And that was the only one that really had some issues.
At least you really made a stand on that one.
Yeah, I mean, people went all over the place with that, so I apologize for that question. And let's see, let's go over 7 though, because I think most people got that wrong for a variety of reasons. And I don't have it paper copied out, so I'll just have to rewrite it. So we were looking at this equation, so N2 plus H2 gave us 2 equivalents of ammonia. And then we were given that chart of values, if you remember. And so you're given something like this, and you had your delta Heta formation, delta G, delta S, and that was joules per mole, 0, 0, 191.6, 0, 0, 130.7, so negative 44.9, negative 16.8, and 199.8. And so most people got like parts of this correct, but I wanted to go over it because I think we forgot a few steps, and then, or people just miss little things. And so this one, what formula, like what was the big overall formula that we had to use? Oh, and it said, change in G equals H minus, and that's change in T though, times enthalpy. So exactly. And the question said calculate delta G at 250 Kelvin. And so the part, so most people at least kind of recognized we needed this formula, and that was good. But then people got tripped up in the delta H and delta S calculations. And I think it was just we forgot minor things like multiplying by however many we have. So for our delta H, remember it's the sum of all the products minus the sum of all the reactants. But that means if we have 2 equivalents of ammonia, we had to multiply it by 2. So a lot of people went wrong there. Sorry, let me pull up my calculator. So then we got, so negative 44.9 times 2. So that was our delta H. So negative 89.8, and that was in kilojoules. And then, so delta S, same thing. So sum of the products minus the sum of the reactants. And so that was another one where people either forgot to do one or both. And so for this one, if it's products minus reactants, you had to do 2 times 198, or 199.8, minus, and then this is where some people forgot, so we had the 3 hydrogens, so then you had to do 3 times 130.7, and then minus our 191. So then I think we should have gotten this for the change in S, but then this is in joules, so then it's only negative 0.184 kilojoules for plugging into our formula later. And so once you had these 2 numbers, then we could find our delta G. So delta G equals negative 89.8 minus our change in temperature, so 250, or our temperature times our change in S. So now that's going to be an addition. So let's see, divided by 1,000. So times 250, and then negative 89.8 minus our negative, so that should be addition. So you should have gotten like negative 43.8 for your final answer. So I think I gave most people like half credit for this one because most people had kind of all the pieces, but then people forgot again to do either the ×2, the ×3 factor, or both. But yeah, overall the quizzes were pretty decent, and I will hand quiz 2 and the 2 quiz 3s that I have back. All right, any questions? Sorry, too many papers to look at. Any questions about anything before we begin?
You divide the joules by 1,000 joules, right?
Yeah, so that's what, yeah, after I did this math here, and I just did it in the calculator. And I can't remember, some people might have messed this part up as well, but I don't recall. It was mainly the multiplying that was pretty consistent. All right, so I have your exam in front of me, so we'll go through it. Should I just talk about it first? I don't know if we'll hit everything. So yeah, I'll just go over what's on there. So question 1 is you have some sort of compound, and then you add 5 different things to it, and you just have to say, will the solubility increase, decrease, or not change? And then, so determining kind of what's true about a spontaneous process or different, given different conditions. So can you identify, like, if something's endothermic, exothermic, or spontaneous, non-spontaneous, what statements will be true, like about S and H and G. I don't want to give too much away. There's determining oxidation states, so we can always practice that. So both with compounds and also with kind of the Lewis structures like we did in class, so the organic compounds. Question 4 is just a buffer question, so that one shouldn't be too difficult, just Henderson-Hasselbalch. 5 is going to be balancing a net ionic equation. 6 is titration calculations of weak acid and strong base, so calculating the pH, and then, you know, equivalence point, all that good stuff, half equivalence point.
Did you say strong acid, strong base?
Oh, sorry, weak acid, strong base. And then, oh, we should do the solubility question, because there's some issues with that on the quiz. So 7's a solubility question. 8 is kind of one of those entropy questions. So determining when something becomes spontaneous. So kind of how we did with this one. And then 9 is just using our dissociation constant to calculate Gibbs free energy, which we may want to go over since we didn't touch on that too much in class. So 9, and then some of them have parts, and the test indicates how many each one is worth. So most of them are worth 10 points, and then 2 of them are worth like 15. So let's do a little warm up here. So we have this compound. So vanadium chloride, tetrabromide, 2 minus. And so just start with this one and see if you can assign oxidation states to all elements. So I'll give everyone a minute or so.
When we are assigning oxidation states, so for chlorine, for example, would you want just the oxidation state of one, or the oxidation state of the 3 of them together?
Just like one individually. And then, like if there was ever a case, like if you had 2 irons in the compound, then you want to indicate them like separately, or
Like if they're not indicated, like Fe3 or Fe2?
yeah, or like it. I mean, it probably wouldn't happen in this class, but I'm just saying if you had some sort of manganese iron weird bimetallic complex or something with 2 iron centers, but
If you're going to do that to this, we need a second set.
yeah, I probably won't do that. So let's go over this one. So we'll leave vanadium for the end. But what's the oxidation state of the chlorine here? So -1. And then bromine, what's its oxidation state? So what group is it in? So yep, so -1, so bromine, chlorine, right? They're all those halogens. And so if these two are both -1, we have an overall charge of -2 here. So what does that make our vanadium? Positive what? Try again. So remember, you can write out the algebra if you need. So write -2 is equal to, so you have 4 bromine. So 4 times -1 plus 3 times -1 plus, then there's just vanadium, so I'll just put X, or you could put V, whatever symbol. Then we have, so -2, so -4 plus -3 is -7 plus X. So then what do you get for our oxidation state? So +5, excellent. So now we'll do the trickier organic compound. And I'll draw it as like an organic structure. I'll give you a hint. Oh, no, you haven't. It's pretty explicitly drawn, though, in your exam. So I think you'll be okay. So see if you can figure out the oxidation states for this molecule. And then if I draw it like this, though, do you know that there are hydrogens on each one of these? I'll draw it more explicitly. So like I said, it shouldn't be an issue on the exam because I think everything's drawn out. Yeah, there's no implied hydrogens that you have to watch for. But I'll redraw it. So carbon always has 4 bonds. All right, so now it's drawn out more explicitly in case you need that. Okay, are we ready to go over this? So let's start with kind of maybe the easier ones. So what's the oxidation state of like this hydrogen here, for example? So +1. And then, so now kind of thinking about it, well, this carbon obviously is attached to the hydrogen, so it's more electronegative. So it took those 2 electrons, bound to other carbons, so remember those get split evenly. So then what's the oxidation state of this carbon? So -1, exactly. And so that repeats, right? So +1, -1, +1, -1. All right, so let's stop there for a second. And then, so what about this carbon? And we can always, right, you can perform your analysis if you're not sure. And so I'm just going to do it right over here. Well, it's connected to 2 carbons still, so it gets half of those. And then what about the nitrogen? Who gets those electrons? So nitrogen, perfect. And then, so nitrogen, it's not shown, but it has 2 lone pairs on there. And so then it would get those electrons. And then it also gets the ones from this carbon. So 1, 2, 3, 4. Okay, so let's go back to this carbon before we get carried away. So then what's the oxidation state of this carbon attached to the nitrogen? So +1. And so you can see that right from your diagram. So remember that formula, you just take electrons in the neutral minus however many it has. And so this is +1. Might as well go to the nitrogen since we drew this, or at least I did. So what did you get for the nitrogen then for its oxidation state?
How would we have known that it had 2, or that it had a little pair?
Because otherwise it's deficient. So then it only has 6 total electrons. And then you know nitrogen, right? It tends to make 3 bonds. And so it has those 3 bonds. Yep, so -3 then. So 5 minus 8 gives us -3. And so now we just have this carbon. So if we do our analysis, so does carbon get any electrons from here? So I see a lot of no's, so it has no electrons. So what's its oxidation state? So +4. Okay, looking good here. And so let's do, so now we just have these 2 sulfurs to contend with. And so remember, sulfur, just like oxygen, is also going to have 2 lone pairs sitting on it. And let me take a look at your exam again. So just to make you feel better, the one on your exam has the electrons drawn explicitly on it as well. So you don't have to worry about this. And so then sulfur gets both of those. And so what's the oxidation state of this sulfur? -2. Excellent. And then so last little bit is this SH group. And well, we had already said that that sulfur would get all the electrons. And so if we split it up, we'll have, again, our sulfur, so that's going to be -2. paired with our +1 hydrogen. And then you can make sure that it all adds up. So let's see, -2, so -1, +3, that cancels. It should all cancels. These all cancel. I have to add them.
Marissa, can you go back over the SH, that little last bit?
So yeah, the SH, I kind of did it quickly. So it looks like that attached to the carbon.
So it took the pair from the hydrogen.
Yeah, let me redo that. So carbon, SH, and then it had 2 lone pairs again, which we didn't draw. And then it took, yeah, 2 from the carbon, and then 2 from that H there. So any questions on that one? And then it should all add up. I was just adding it up over here. So 1 plus -2 plus -3 plus 1 plus -2. And so this all cancels. That should work out. All right, questions about this? So let's look at solubility, because I'm looking at your exam, and your solubility question is kind of difficult. But I also wanted to go over the quiz, because it was like half and half of what happened there. So you had for the quiz, this was the take-home quiz, you had the KSP of silver chloride is 1.8 times 10 to the -10. Then it asks for find the solubility in grams per liter. And so this was relatively straightforward. I'll just write out kind of the scratch work and remind people of the process, because again, your exam is trickier than this. So you have kind of what I put S here for our solid chunk, then it disassociates to 1 equivalent of silver plus 1 equivalent of chloride. And so you have that SS, or you could use the variable X. And so then if you were solving for the molar solubility, obviously you get S squared equals your KSP. And so that was A. So that was 0.000013, but that's in molarity. And so I think I gave people like partial credit if you at least showed your work and got there. But then of course I asked for it in grams per liter. So then the last little bit was just multiplying it by the molecular weight, which I believe is like 143.32 grams. And so that would have given you the correct answer, which was D, 0.0019. And again, the unit on that is grams per liter. So that's the process. Now I'm going to give you your exam quiz, and then I'll have you attempt it, but then try to determine kind of what's different. And there's also other parts to it. And so we'll go over it all, but I want you to at least think about it. And so your question is, the solubility product constant. And I want to make sure everyone knows how to interpret this question. So the solubility product constant for aluminum hydroxide is 8.3 times 10 to the negative 32 molarity to the fourth. And so determine the gram solubility of aluminum hydroxide. And this is kind of the tricky part. In a solution buffered at a pH of 10. So at least take a moment, try to figure out what little parts you might need. Don't forget what happens when you disassociate. There's 3 equivalents. Notice this m to the 4th. That's supposed to at least kind of help you of like, oh yeah, that's what's going on. I'll give everyone a few minutes.
The solubility product constant is KSP, right?
Yeah, exactly. So that's kind of the first part that I wanted to make sure everybody understood what the heck solubility product constant. So yes, that is just KSP. And I'll still give you a few more minutes to kind of play with it and how you might set it up. We lost our time. Oh, there it goes. So let me hear your thoughts. So how did you kind of set this up, or maybe even writing out the KSP in terms of some variables, or? And then, what should we do about this buffered part?
So I was converting the pH to OH and then trying to solve for the concentration of hydroxide ions, and I got 10 to the negative fourth.
Yep, so that sounds good. And so let's go through that so everybody can follow. And so we have this confounding factor, and so the relevance, and maybe let's just write out kind of our solubility product that we're looking at. So we have aluminum hydroxide, right? We know it disassociates to make aluminum, plus 3 equivalents of hydroxide, so we have that set up. At this point, you may want to just kind of, write your variables, so your solid, and then S, 3S, and then don't forget for KSP, you also take it to the power, so that's going to be S times 3S to the third. So that's kind of your general expression. And so yes, exactly. We are at a pH of 10. We form hydroxide, but you know that if it's at a pH of 10, then it's basic. And so that's why Vaughn went ahead and went from pH to POH. So then if the pH is 10, what's the POH?
It's 4.
So 4, and I saw some fingers of 4. And then we can just take, again, 10 to the power of that to give us our hydroxide concentration. And so the relevance of that is then we have to put it into our Rice table. And so we have our reaction, and then we can put our initial conditions. So initially, we're just going to assume, right, we don't have any aluminum because we haven't disassociated, but we do have a starting amount of hydroxide, that 1 times 10 to the negative 4. So that needs to go there. Then we can do our change. So of course our change is our plus S plus 3S from this disassociation. And then at equilibrium, right, that gives us S, and then 3S plus 1 times 10 to the negative 4th. And so once you're here, this is a good place to be. So then you can plug this back in to your KSP here. And so now you just have S times 3S plus 1 times 10 to the negative 4th cubed is equal to your KSP, which is at 8.3 times 10 to the negative 32. And so what assumption can we probably make to make things a little easier for us?
That the KSP is so small that our change of S doesn't really matter.
Exactly. So KSP is small, and we'll make the map easier. So let's just ignore this 3S factor. So now this simplifies to S times 1 times 10 to the negative 4th cubed is equal to our KSP. And so now at this point we can solve. Except when we solve, right, this gives us molar solubility. So I'll plug it in. So let me know what y'all get as well. And you could actually practice your mental math skills. So 3 times 4 is -12. And then dividing, so then you're subtracting. So -32 minus a -12 is like +12. So that gives you 10 to the -20th, which is what your calculator spits out. Make sure you enter in everything correctly. As always, if you need help with your calculator, just ask. Always best to use these e's. So 8.3 times 10 to the -20th. So that's molarity. So did everyone get this at least? And so from there, we just need to convert it to grams per liter. And does anyone have the molecular weight? What did you say, 78? Point what, or?
I think Dorothy says it's 78.
No, that's also what I have written. It's just 78, but I didn't write anything after.
0.00.
Cool. If someone wants to add it up and give us a different answer, that's also fine. But so roughly 78, and then so we just take that times 78, and so that gives us about 6.47 times 10 to the -18 grams per mole. Oh, grams per liter, sorry. Good catch. Grams per liter. Questions about this one?
Is it say 15?
Oh, -18. Oh, sorry.
So the concentration of the OH was 1 times 10 to the -4 because the pH is greater?
Yeah. So then you could just plug, because you have the POH equals the negative log of H plus, and then if you take everything 10 to the power of, so then hydroxide equals 10 to the negative pH for your concentration. So yeah, that's how we got it there. All right, so you'll have to do that on your exam. Hint, hint. Let's see what else is tricky. So let's try what I call question 9. So this is 9 on the exam. And we'll do a very similar question. And so we're looking at this reaction. So HF plus water gives us hydronium plus fluoride. And so at 30 degrees Celsius, the dissociation of HF is 5.7 times 10 to the -4th. And so now what is the delta G for this reaction? So take a few minutes, at least see if you can find the formula. It should be back in your notes. Oh, and the R is, remember, the 8.314 gas constant for joules, moles, Kelvin. I did not provide it on the exam, but maybe I should, is what you're telling me. I can add it. I'll make a note. I'm sorry. So let's see. Are we ready to go over this one?
Are we using the LNK equals delta H reaction, this equation right here?
Probably like a better form of that, because that's more for like graphing. So I think you found it now.
This one?
So who wants to give me the formula that we need to use?
Delta G equals negative RT natural log of K.
So perfect. So did everybody find this formula? And so from here, it's just plugging everything in. And so like we mentioned in lecture, although we did kind of rush over this part, so that's why I wanted to do this question. But all it is, it's relating our good old equilibrium constant back to now delta G. And then, so someone already asked what R was. So that was 8.314. And then what does T need to be in?
Kelvin.
So Kelvin, so 273 plus 30, so 303 Kelvin. And then I like that you said natural log, so exactly natural log. So again, just make sure you plug that in correctly on your calculator. But at this point, I think everyone should be good to plug your numbers in. And so somebody can let me know what they got. as I plug it in. So do we get like, it should be positive, I just didn't, I'll do that. So I see some nods, so around like 18,000. Of course, this is joules, so I would convert it to kilojoules. I don't think, yeah, the problem doesn't specify, but I just like smaller numbers. But either way, you could leave it in joules, convert it to kilojoules, just label your unit, so 18.8 kilojoules for delta G. Questions on that one? Let's do another math problem. Just comparing it. And so we did one of these in class, so we'll do another practice. So a reaction has a change in enthalpy of positive 320 kilojoules per mole, and a change in entropy of 101, and that's joules per mole. So at what temperature does this reaction become spontaneous?
Bless you.
Think, think. I like how they just sent us an email that the Wi-Fi is back on, but then the clock says it's offline. So.
Maybe the clocks need to be manually reconnected. Like it'll say that until someone comes in and goes, doop, doop, doop.
I doubt it, they're pretty remote. That's the whole point of those things. Campus messaging system.
Like pagers.
All right, do we have a formula for this one at least? And if you're in the chat, you can always chime in as well.
We're looking,
We need to make this, the temperature times S.
yeah,
It's 101, right? So it's a negative, right? It's minus. Need to get temperature in Kelvin. That makes that 320. Equals this. To get delta G under 0.
I mean over 0.
So what's the formula?
Delta G equals heat of fusion, not delta H, sorry, minus temperature times delta S.
So-
That's in joules per mole, not kilojoules per mole, so it's going to be a huge number of D.
Yeah, so good observation. So joules, kilojoules, and when is G spontaneous? When it's positive, negative?
Positive
Try again.
0.
Oh, 0 is equilibrium.
Oh,
And then, so once it's negative, then it's considered spontaneous. But we can use 0 to set up our math, since that'll be
That
bright
is
at
when
the
it first becomes spontaneous.
Right,
Theoretically speaking.
exactly. So then, we'll set this up, and again, converting this to kilojoules, so 0 equals 320 minus whatever our T is, times 0.101. And so we got to do some algebra. So what do you get for this?
You don't need to do 0.101 times.
So did you get this ridiculous answer as well? Negative though? Because you move the T over.